going to talk on the following topics. There's a lot of buzzword about circular economy. I'd like to put that briefly into perspective of a metallurgist. You heard from the intro that that's what I've been doing since 1982 as an engineer. Basically also speaking about digitalization, which is of real importance as well to our fields, how that fits into the big picture. Just a few sheets on design for recycling at the end. So bear with me. As I said, I'll try to keep it as brief as I can. Try to be provocative, and perhaps there are some questions coming up. And there's a literature in the end, and you'll get all the sheets, so you don't really have to write down anything. So this picture will appear a few times, but I just like you, as metallurgists, as process engineers, to go and have a look at the documents out there. And when the EU started with its circular economy talk and jabber, sometimes I call it, they just looked at the materials, but they never really looked at energy. You can have a look at the documents, go and have critical look, and you'll see that there's a disjoint. Any process engineer that designs a plant will always look at the energy and mass balance at the same time. And it's interesting that there's a hype in the EU that actually missed out on that point totally. But nevertheless, as metallurgists, we've always recycled. It goes back thousands of years. Huh? If there was value in the metal, you would recycle it. If it's not, you wouldn't. So for us, it's nothing new. We've always been doing this, really. But it's just a paradigm of importance, but it's got some very important answers in it as well, of circularity, of making sure that things can be recycled in the first place, and that there are limitations which we have to be aware of. Just some data. The world city consumption of materials will be around 90 billion tons by 2050, according to the World Economic Forum document published at the forum meeting earlier this year. Of that, a pretty large number of waste has to be recycled in this. So we're speaking about circular cities. We will consume materials, metals, energy, but then we want to forget all the heavy industry. But you need that. You need that in Europe, you need that globally, and you need it to run pretty well. And you have to understand that very, very well to minimize, ultimately, this residue stream. So for me, process metallurgy was always not only to get the valuable elements, but and metals is actually to manage the residue and minimize the risk that you have with that. So this bit here, which originates all along, unfortunately all the circular economy pictures have just positioned it over here. So we engineers, when we do a e-waste recycling plant, now we have to deal with it. But in fact, it really starts already here with the product design. So what we've done, and I'll try to show this to you very briefly, that we've linked digitally from here to product design and to recycling, all in computer models. Ultimately, that's where life is going. And as I say, we can do it, but there's still a strong lobby that's trying for us to tell, this is all too difficult. Because the real problem is the two easy models that have been sold to the EU are so simple that they print a rosy picture which is possibly not economically viable. So we as process engineers have an extremely important task to put the truth out there. So let me start with this. You all know old Elvis, rock, metal, you know probably heavy metal. You go to discos and stuff. You know AC/DC from Australia. Okay, see there's some of you. So I've just tried to bring together, just keep this image in your mind. From rock to metal, energy. It's there. And then my family are all musicians, so I put old Mozart in there as well. Because of his beautiful music as well, and simple music, honest to truth music. And that's what this whole message I'd like to leave with you after about an hour that I'll be speaking here. To just start off, and this is key to the message. And I've been saying this for many years. About 25 years ago, we published a paper, Metallurgy or pyrometallurgy is the closer of the loop, long before circular economy was a buzzword. Pyrometallurgy or process metallurgy is the closer of the material, at least the metals and element and inorganic loop. So I call this the metal wheel. This is the metal wheel of society. If it's gone, we cannot run a circular economy. So in this room, Atlantic Copper is involved mainly over here. It's an extremely important bit of the metal wheel. There's zinc and lead, steel, aluminium, light metals, rare earth, all those basic elements and materials that we need to run the circular economy, the renewable energy systems, etc. But interestingly enough, 20 years ago, there was a lot of pressure on zinc because somebody had found out that zinc is poisonous for some little animal. And then my colleagues told me, what the heck, what's happening? So how can we stop that? So we came up with a metal wheel to explain the following. That with each metal, zinc and lead, you get a whole variety of co-elements that are passing along. Any geologist knows this, any process engineer knows that, but there are a lot of people that don't know this anymore. So in a way, we also tried to save zinc 20 years ago, which we did. With a lot of people started working together. And incidentally also, it is the supplier of indium, which became so important since these last years and all the flat panels we use. But then there are also a lot of elements that are not processed in the zinc plant itself, but go further to other plants that are around it to recover them as well. You can see nicely here that the copper and nickel and zinc and lead, tin, the non-ferrous route has got a very high propensity to recycle. The metallurgy is great for that. It's not so great for these segments, for instance, steel. However, if you manage the steel well, you can get the alloy elements, these orange ones, into the right alloy, and then you can make new alloy. Same for aluminium. So it's about managing the minor elements, not the major ones. In recycling, it's about the minor ones as well. And you have to manage it very, very well to ensure that this metal wheel turns. Then ultimately, you will always lose stuff. It's just thermodynamics. It's the way it works. You know that from your theory. And few people still seem to recognize and remember this. So we try to come up with images to tell policymakers what the heck's going on in the real world. So the first message, this wheel is at the center of this energy. Hey? If I'm looking at all these renewable energy solutions, they need metals from here. But they will also come back through the recycling chain back into the system. So if we don't have this wheel turning, we are buggered. Quite simple. And it seems to me sometimes that policy does not understand that anymore. And you guys have to make sure that policy gets out there. So in a recent discussion, we came into the point, how do we explain this? And I'll come to that in a moment. So here's one drawing that comes up in a new journal paper, very high impact journal, the annual reviews of materials research. So it's getting to now to the materials research people to make sure that you can't just substitute stuff. You can't just take stuff away. Because if you're taking copper and nickel away, this whole segment disappears. If you would do away with Atlantic Copper, Urubis, and all that stuff here in Europe, this falls away and the wheel cannot turn anymore. And that's pretty obvious. And it's surprising that you may say this is a no-brainer, but you go and explain that to the policymakers in the EU. So interestingly enough, you can't see this. The resolution is not good enough. There's a European Chemical Association has put lead on a list for prohibiting its use in certain applications. Now that's extremely important that you as metallurgists sitting here have to be vigilant of this type of stuff. What does that mean? If I take lead away, I'm taking the whole lead segment away. It's not just lead. I'm destroying the know-how to deal with lead and its metallurgy. So that's why we drew this bike going the wrong direction. And this is actually in a policy document that we submitted and will submit soon to the EU to ensure that they are very mindful of the complexity of lead metallurgy, and they just can't just take it out of the periodic table, because they will destroy a segment and the wheel will not turn, and the biker will fall on his or her head, as it is clearly shown there. So ultimately, we want to go the right direction. Now, this is nice to draw these pictures and showing the complexity of our metallurgy, and I always get told, don't say our metallurgy is so complex, but it is. It's not just recycling of wooden chairs. It's recycling of very complex products, and pedelec is becoming a more and more complex product, and we have to deal with those materials, the lead battery or the nickel, the lithium ion batteries, etc. So just before I go on, so just to summarize it, this is a little event which I was involved in that sort of summarizes this first aspect very well, and people are sort of starting to understand. But still in the EU, then they want to cross out lead from the periodic table.
What is a byproduct metal? So there are clearly some metals like copper that are almost always produced entirely from copper mines, and so they're very clearly not byproduct metals. There are other metals like selenium, mostly from copper, but it's a byproduct. There aren't selenium mines. And then there are a few metals, silver for example, where there are silver mines, but most of the silver comes as a byproduct from zinc mines, lead mines, gold mines, copper mines.
But it is a challenge as we go deeper and grades get lower, ore bodies get more complex. That becomes more important to understand what's in the ground. And having said that, we're getting much more sophisticated now. And as an industry, we're getting deeper and more complex of an ore body, so that real-time interpretation of data is more key if you want to close the loop.
But we try to recover them all in the best possible way we can, either as a product, which we sell.
We need to better understand, what's in there and are the detection limits low enough that we can really find out what's there and be more confident about how to recover them, and if it's economical as well as if it has some strategic advantage for the industry.
We believe that there should be a balanced approach between primary and secondary, so you need to improve the primary, but you also need to improve the secondary. With Horizon 2020, there can be pilot projects.
If you really want to make circular economy work, you need a really vibrant and high-tech copper metallurgical infrastructure. So not only is copper the supplier of important metals, but it's also the solvent to capture them back and then in refining release them.
It's very important to note that in Europe, actually, the few remaining smelters are highly integrated with the rest of the non-ferrous metal industry, so that each of them is really unique in the way they process already the materials and take out most of the elements that they receive.
So the tandem of copper and lead and zinc and nickel metallurgy as such are basically crucial for a circular economy.
We have, even under Horizon 2020, a call on recovery of byproducts, both from primary and secondary raw materials production. So we believe that enhancing the recycling rates of byproduct is very important. Copper can be an important carrier, and there can be synergies in having production of copper combined with byproducts.
The materials scientists are so good at choosing the very best material. And once you've done that, any substitute is something that degrades performance and you're unhappy with.
So in summary, this is just the first bit, and it's probably a no-brainer to you guys, but I always try to bring that up front to show to it that we as process metallurgists are really at the heart of the circular economy. So, but then I asked the question, will we ever achieve circular economy? The theory that you guys are taught are really at the heart of really estimating that well on a fundamental point of view. So what I'd like to show to you in the course of the following sheets is, okay, here we have one of our smelters that, I speak of ours because I was a long time at Autotech, but I'll speak a bit about that. Then I will go to just 1 or 2 sheets and some theory that we are actually trying to understand the fundamentals of these processes, the interface processes which lie at the heart of the circular economy. If you don't understand how masses and energy is transferred between different phases, you cannot optimize that system. So whichever reactor system it is. And ultimately also just measuring stuff. And I'll show you some videos to show what we are doing in this field, and which is really the exciting part of our field. There's still so much digitalization and understanding to go on. It's really, in that sense, also very exciting to be in. So how will we ever reach circularity? It's obviously, we have to understand it in multi-dimensions. Now, there's the circular economy gurus that speak about all the service models and all this stuff. And I always try to get back with our feet on the ground. Now, see, we have all these mines shown here, all these rocks. We've got our feet on the ground, so we understand the system. But if we want to do that well, we need tools. I'll quickly show to you some where we are at the moment. I won't go into depth. I just want to show to you where we are already. What's out there and where we have to go. So we have tools with which we can understand the thermodynamics, we can do the flow sheet, and we can do exergy analysis. And I'll show that to you, as I said, in a moment. We can do the environmental footprint from the same software. I'll show that to you. We can link that to MATLAB and do all kinds of fancy stuff, play around and do optimization. And then obviously we can do techno-economic analysis, which is part of engineering. If the plant doesn't work, the circular economy model doesn't work, or whatever business model you do, then, well, then you're lost in this anyhow. So I'll show you also CFD, computational fluid dynamics, briefly, just to show that there's a lot of depth also to be done. And then ultimately also, 30 years ago, I did my PhD on artificial intelligence. At that time, we were laughed at. Now it's buzzwords. There were big projects and everybody's thinking of AI. But we've already used AI 30 years ago to optimize furnaces. The problem was sensors, measurement, just getting the stuff in the computer and getting large bodies of data so you can do some good stuff with. And we learned some hard lessons from that. I won't discuss that now, but you can look on my ResearchGate page. You'll see papers from 1990, 88, way back, that we worked on these things. So, how do we digitalize this system? This is my other important message, and this is why what you get taught in this course, being here, makes us so, how shall I say, in a way special, because we understand these facts. You all know this is a copper ore. We can use fancy, sophisticated tools to understand its mineralogy. We can do mineral liberation analysis. You will probably all know what that is. We can take this information and we can stick it into a process model. And we can simulate certain plants. And some of that stuff, it's not where it should be, but we're working at that. And I'll show that to you in a moment. We link this type of information to the smelter, and I will use the TSL as a smelter. I can use many others, but this is one which lies dear to my heart, just as electric arc furnaces also lie dear to my heart, submerged arc furnaces as well, but I will concentrate just on this one. This just gives you a bit of a size indication of how big these pots are. About 20 meters by 5 meters is the largest one that we built. And we have control systems that run that and link basically that to here. And there's still work to be done here, but we get along. But then you have these design people underneath here which take these metals and create a fancy product. And then they start using Excel sheets to understand the system, to design a project. And in the end of the sheets, I will show to you what we did for this specific example, the Fairphone, to show what its true recycling rate is. Not what the people got out of Excel sheets, but what we used with the same tools that we use here, we used here as well. To ultimately understand, if you want to describe the system over here, you need to understand its mineralogy. Now, mineralogy is clear for this bit. But we, for many years, have started to call this also mineralogy, but it's just a designer mineral, very complex mineral. But you have to know also how this is composed. But the designer sort of knows this, but they're not making available that data. But I'll show that to you in the end. So ultimately, you'll see the worlds. If you really want to understand the system, you have to know the mineralogy of the system. You guys can do that. Our industry can do that. There are a lot of people out there that are doing circular economy, blah, 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 but they can't do this. And then they tell us, this is all too difficult. We say, but we're using it. And, well, it's just amazing what's out there. What we also do, and this is some very nice further development, is we have got MLAs in our department. We've got 3, as a matter of fact, in Freiberg. But we've also got a 3D tomography equipment. So you can start using scrap and analyzing it in the same way as you're doing that to feed it into these types of models. Not only the element and the compound, but how it's linked together in its mineralogy. If you can do that, you can understand the loss from the system. You can understand the entropy creation in the system. You can understand where is the most exergy destruction in the system, and then you can start optimizing it well. And then you can do design for recycling. But when I tell that to people out there, it's difficult. But I'll show to you our approach that we use to make that more palatable to a wider community. So this is just a bit of a quick picture. I won't go in too much detail. It just basically shows between these different sections here, these little colored sections, what plays a bigger role. So I'm just going to focus on engineering, metallurgy, and that type of stuff, footprinting. But there are other stuff as well that plays a role. It's not just thermodynamics that plays a role. It's also consumer decisions, consumer behavior. Do you want to throw your Fairphone or your iPhone away or not? How does the market work? And what do the policy people do? What tricks do they show into the system? Because they're not informed well and they make some decision like crossing out lead from the system. And that sort of buggers up the system big time. And we have to sort of mitigate that with facts, with real facts and real numbers. So this is just the objective of this sheet. You can have the sheets at the end of the talk, but these are all factors that play a role, and there's some more as well, but I'm just going to focus on the hardcore process engineering bits. So where do we want to go? Ultimately, and this is a picture that also comes from my colleagues in Autotech. We've also been speaking about these aspects. So you have your virtual plant, and ultimately you have models that are running in various bits and pieces, but you have to parameterize them, you have to understand them to really predict things ahead. So these are typical furnace and applications, and you have the process designer here with its tools, and you have the process operator also working with tools to interact with that. I would like to show to you in the next sheet some of these tools. And I've been involved as I worked for Osmelt, and then Autotech bought Osmelt. And in 2010, I phoned my colleagues in Finland and said, hey, Antti, we have to do this and this with the software. And I'll show to you what we've done for the last 8 years. And we still have a few years ahead of us to do some work. Obviously, we want to optimize sort of key performance indicators. We want to have the footprint. LCA means life cycle assessment. Control emissions, efficiencies, availability of the plant, the values of what we do, etc. These are all aspects which we can sort of quantify if we have good models. So this is the tool that I've just been intimately involved with and still am. So some of our students are adding the depth to further advance stuff, but this is the platform. Let me just show to you where we are with in specific case with copper. This is nicely copper. Let me show to you what we've done. So as you see, just a tool that interacts with various, gets information from various sources, has databases from which it takes its thermochemical data, its mineral data, etc., and drives the simulation platform to model whole systems. Here to keep it, as I said, in copper. I'll show to you what a student of mine has done. Oh, it's not just mine. It's a student from Zaragoza that is part of a European training network called Socrates, where there are 15 PhD students. Alejandro has created with me this model to firstly just show that we can evaluate the whole copper chain, but it's interestingly enough that slowly the EU is also understanding, and Alejandro will analyze each of the other PhD projects if they are worth what they promise. So you start teaching young people when they come up with a new idea, put it in a simulator, try to get the economics of it, understand its footprint at the same time, get its exergy destruction at the same time, and understand what the hell you are doing. So Alejandro is checking all the projects, which is, I think, a first one in any project at EU level, that you're actually not just having LCA at the end, but it's actually analyzing the projects. So this is the first example. We had to show how the method works, and we implemented it in HSC. So what we did, and these are just quick, some flow sheets. Don't look at them. You can look at them in your own time. Where we are at the moment, we took a plant, 6,500 tons per hour, 30 elements, with all the residues and stuff that are created, starting from the mine. We recently published this, and you see the authors involved here, the guys from Zaragoza, Alejandro Variaz-Lama, and then a few. Hopefully my Spanish is not so good, but anyhow, you could see some of the Spanish colleagues, or Valero, and then some Odotech guys and us. So we just published this, and it's been a long learning and long years to get this where it is. So we can do a simulation of a whole big part of the circular economy on a mineral base, understanding the energy flows, but also understanding the entropy flow. Now, you know, and for me, coming from the metallurgical side, I was always trying to get the attention of, sometimes I just have to call them snake oil salespeople. They're selling us some nice story. And then I ask, what is the entropy flow? And they look at you. I just reviewed a paper this morning in the plane when I came here. And it was all about circular economy. The first thing I did, I searched for the word energy, entropy, exergy. I couldn't find it. And this was an impact journal 4 or 5, something like that. So you see what all this nonsense gets published. So here we try to now, here's the paper, guys. Don't tell me it can't be done. So ultimately, here's the smelter. So we connected 11 flow sheets. This is flow sheet number 1, the flash smelter. You can see over there, if you look, you can't see it, but if you look at the sheets in your own time, you will see that this is all compounds. Then we have the sulfur capture, the sulfuric acid plant. It's all generic. We took it from the Handbook of Copper, the Biswas and Davenport book. So we didn't want to jeopardize anybody's IP. We just wanted to show, hey guys, we can do it now. So we took the precious metal recovery. Here are the TSLs for dealing not only with primary, but in this case, secondaries. I drew 2, or I asked Alejandro to take 2, because then you have 2 oxidation states you can work with. But you can do this in 1 reactor. You can have a 2-stage process. But you can separate the metallurgy, so you can separate more metals from it. But then what we also did, we started modeling the zinc and lead flow sheets. Here's the classical roast leach electrowinning flow sheet. Here's the roaster and all the neutral leach and hot acid leach, etc. And also lead processing. Now, TSL, once again, has been used as well for lead processing in either 1-step, 2-step, or 3-step processing. And once again, we have the refinery over there. So what you can see here is that we are trying to start modeling the metal wheel to show to policy what makes sense and what does not make sense. And also, therefore, strengthening the role of copper in this case, zinc, lead, to show if you take it away, you're destroying the system. then you cannot have circular economy work. And sort of this summarizes the wheel with a segment not there that the wheel can't turn. So we can show that also, not just make nice pictures, but actually show where all elements go. Not just one element, all the elements in the system. So what can you get out of this? And this is then interesting as well, because you can then get the exergy flow here of all the different steps. In this case, we've already expanded the model to 160 processes with 600 streams and, well, I said over 20 elements. It's around 30 elements. You start understanding the exergy destruction at the power station and also due to the minerals. If I'm taking a chalcopyrite and I smelt it to copper, I'm destroying a lot of exergy. But I'm using the sulfur as a fuel. That's why I have very little, it's a very small amount of power being used and therefore exergy destructed at the power station. But what I can also do, I've linked it to the LCA tools. In this case, there are some well-known tools which you can use. You can take the whole flow sheet and export the information now to determine, for instance, the global warming potential for different options. So it's quite a unique tool, and now nobody can tell me anymore at the EU or anywhere, this is too difficult. The interesting thing, Alejandro is a mechanical engineer. So he learned metallurgy in a crash course with me through simulation. It's such a beautiful way to hands-on to learn the detail. So obviously he made errors, but I managed that. So it's quite amazing that he could do it so fast. And so there's another guy also from Zaragoza, Jose. He's Ecuadorian. He's also learned this on a simulation base. So we can get people from other directions into our field on the back of good tools and with a message as the one shown over here. Okay. That gives you a bit of an idea of the digitalization platforms, at least very brief on a simulation way, how we can develop flow sheets. How do we manage the flow sheet? Where do we put what reactor is of extreme importance for young engineers in the future to be part of? That's really creative. It's really a creative exercise to create a flow sheet. It's like a painting, really, at least for me. If you see this flow sheet, they say, this is great, this is music. Or that's just crap. You know it, but you can show it, and that's beautiful, and at least that's what excites me. So hopefully I'm not too a nerd in this aspect. But so, let me go back. So I sit in the plane, or even my secretaries say, hey, are you doing your nerd stuff again? You're doing your process models. So I sit in the plane and do models. But anyhow, yes? Yes.
It's a brownfield plant in
sure.
our case.
Can I go to the next sheet? I anticipated perhaps this question.
It's not so difficult if you have digitalizing the plant. If you don't have all the data, it's impossible.
Yeah. But you can also, in some way already, because the theory is already developed, you can also get away with not just using plant data like we did here. But may I also add, yes, if you have a standard plant and it's there and it has cost many millions of dollars, and now you have to do a new investment, it's going to cost you a lot of money. So which technology would you put where? So here's an example which did that. It was a brownfields solution. I still was involved a bit in the metallurgy of, or not a bit, I had very much to do also making this lead smelting TSL work. There's Plovdiv, which is part of KCM KCM, which is the website is over here, is a lead and zinc producer. Had a old plant, and they decided to cut out certain old technology, and they put in a TSL over there. So it was a brownfields example, and they put this nice TSL over there to create a certain amount of flexibility, clean up the system, and be able to deal not only with primaries, but also residue and secondary material. But so it's a decision if you want to go that way, or add something into flow sheet, but then the question is, what do you add? And that's the takeout rather. If you've got a brownfields plant, do you want to expand? Do you want to become more flexible? Then the question is, what technology do I buy to make it more flexible? And where do I put it in my global operation? And so that is the real message. And for that you need the flow sheeting to understand that flow and the business case for you. But anyhow, that's what happened over here. So I made a decision. I don't have a picture where you can see the brown fields, but it was pretty brown. And you have this white building in the new one, and it's working pretty well. So I was there just about 4 weeks ago, when we had our TSL user meeting for all our clients. It's a lead, really lead smell, zinc lead combinate. And they have a valve kiln as well, so they have flue dust. So if you deal with all those cycles, you can do that. So luckily, as I said, there are still some people in Europe investing money in new plants. Look at the next sheet. Okay? Where are the plants being built? At least this is what we built. And I always show this because it shows something very worrying. Europe speaks about circular economy, got great metallurgists, great plants, but we should maintain that. And if we can manage to keep the core of the metal wheel, we can deal with the circular economy. If not, well, these guys will do it. Simple. So as I say provocatively, the Silkway will bring the cars, and the empty carriage will take the empty used cars back. You know the Silkway, huh? You've probably read all of that stuff. So we get a choice. We can speak about circular economy, or we can make it work. And we have the opportunity. We've got really great knowledge over here in Europe. So the newest plants that are just running, it's also interesting statistics that the Nearstar plant, which was built by Odotech, is a new lead plant down here in the vicinity of Adelaide, Port Pirie. And then there's a new smelter being built, Timar Tin, which would make then TSL producing 65% of world tin, which is quite an interesting statistic. And it's an interesting message. I give that as well, because TSL is extremely nice for fuming stuff. Tin you can fume. Some of the nasty stuff that is in our concentrate we can fume off. So if you manage that well, you can use TSL for that very well. If you want to do other stuff, you can use other technologies. But you have to know that detail to make a good selection of technologies. So you can take the flow sheet and put in different technologies to see how you can manage the flows of materials in your system and in the circular economy, in Europe, in your company, or wherever you will work in future. So here's once again the reactor, just to give you some dimensions. As I said, about 20 meters, 5 meters inner diameter, and we have built plants up to 1.5 million tons per annum of copper concentrate. This large one is for copper. The lower ones, there's a range of different applications. The smaller ones here were done for slimes, sort of precious metal slimes, refining in small TSLs. Those were the beginnings. But this is the largest one in China. Okay, so
Sorry, yes, one furnace?
What? Just one furnace, yeah.
One furnace?
Yeah, making matte. So it's, see the TSLs are, the flash smelters are even larger. The largest ones, as you know, 400,000 tons per annum in China. The direct flash converting, flash smelting, flash converting. And this is about 300,000 tons. It's low grade. So the interesting bit of this technology, of this smelter, is that it can deal with dirty concentrates as well. That's a value, because in future you have to look at that. You'll be more competitive if you can deal with the bad stuff as well, and you can deal with that in your flow sheet. So let me get some to the theory bit, few sheets. I'm keeping an eye on my watch. I want to keep your attention rather than blinding you with many sheets. So just to show it to you what we are doing at the moment in Freiberg. So I'm sort of at the last 5 years of my career, and I just thought, well, how can I bridge between university and industry and make sure that young people come to our industry, which I hopefully are you guys, all of you guys, to make a change to society. Here in Freiberg, we've got a pilot TSL. We have in Melbourne, we have a pilot TSL to test a few stuff. We've got a few furnaces here to do well-controlled smelting experiments looking at distributions of elements. But, you know, a TSL is not an equilibrium. It's all about kinetics, mass transfer, heat transfer. So you have to also measure kinetics. So here just a quick, for my colleagues, if you've seen it, sorry. If you've not seen it, have a look again, 3 minutes. Okay, you see, it's a beautiful piece of equipment. If you know your metallurgy, you know mass transfer, heat transfer, you know slag chemistry, you know the kinetics. You can do pretty much. Just a few pictures to show some of the applications. Here's Xi'an, China, which processes zinc residue. Why? TSL, as I said, is beautiful in pushing reactions to the gas phase. In other words, you can fume off zinc, silver, lead, indium, germanium. All done. We still have projects. We spoke about it over lunch. We have all these beautiful EU projects and say, hey, but it's been done 20 years ago. It's already operational. So people seem not to know this stuff. Then I've been very intensely involved with this smelter, Dawa Holdings. It's an e-waste smelter. Interestingly, the guy that opened the mine comes from Freiberg. It's interesting. In Japan, up in the north, prefecture, can't remember exactly which one it is. This is the TSL now operating, which has replaced this junk here with this one. And then processing e-waste, residues, all kinds of stuff. Part of the Kosaka or the Dawa Holdings company, which is labels itself, go and have a look at its webpage, as a circular economy company. It's actually making it work. Rather than talking, they make it work. And they don't just do e-waste, they do a lot of other materials. Do yourself a favor, just have a look. I was once there in the winter time. Here's beautiful snow. In the spring, you'll have these beautiful cherry blossoms as you have in Japan. Beautiful, but you can hardly see the smelter. It's clean. It's in town. It's in Kosaka. So it's a very, very nice application. Doing e-waste recycling on a copper base, dissolving the precious metals in copper, dissolving the copper, the raw copper, to recover the precious metals, produces a clean slag in a reduction step, all in the same reactor, which is quite nice. So I spent some time with these guys in my past life, not too long ago. I've mentioned also to you quickly tin. I just focus on it. The leading tin producers, most of them are TSLs. And the newest one is this Indonesian, Timah, which adds to this one also about 40,000 tons per annum of tin. So in addition, quite significant. So, as I said, you can deal with it. All I'd like to leave you with the message, if you want to close the loop, you need reactors, you need to understand the metallurgy, you need to understand the depth of these. So another one is Pgm Processing. This is a plant built by for Anglo Platinum in South Africa. It produces, in this specific converter, it's a matte converter, it's not a smelter, it's a converting of matte, produces, or put it this way, 30% of world PGMs pass through this reactor. And it's quite significant. There are two of them, so if one breaks down, they go to the other one. So here you know that primary metallurgy is also still there to deal with the PGMs, platinum group metals, which come out here. And they are dissolved in a nickel copper matte. Okay, and this is the Port Pirie one. You can also look at the web page where they are now at the moment for more detail. So this is just enough of the technology, it's there. But the good thing, or the creative thing, is where do you put it? How do you use the technology? Not this one only, but all the other technologies to really close the loop. So how do we understand this workhorse? I call it just workhorse of the circular economy. We've built, as you've seen, 65. Then there's the Extrata variant, the Isosmelt, which is, they've also probably built about 30. I don't know the exact number. Say there are about 100 TSLs worldwide for copper, nickel, lead, PGMs, e-waste, etc. It's quite significant technology out there that is used. So let me just quickly show to you some. If you want to really understand the depth, this is what we also do. We as professors, we also have to probably understand stuff as well. So here, specifically an example, we've just submitted that papers looking at, and we've published papers on the past. If you look in metallurgical transactions, you'll see some of our papers on this. But we are going further with it to understand what the effect is of viscosity, surface tension, density, etc., on the bubble and the splashing, and therefore also the mass transfer. So there are few people out there that are really doing CFD in our field with this intention to understand that and really understand where you have to go, how you can use the technology best. Interestingly as well, there's another project which is actually measuring on our TSL in Freiberg, measuring with a lot of thermocouples the heat flow, also never been done. It's now being done because I have the money available to actually push this, because I feel I know where the research has to be done to advance the technology to its limit, to enhance the resource cycle to its absolute limits. Interestingly enough, what's also done, and I'll show you a video in a moment, is to actually look at how bubbles are flowing in a liquid. Now usually this work is done with water. In this case we're doing it in metal. So would you know which metal alloy this would be that has a melting point of minus 19 degrees and is actual liquid at room temperature? Can you guess which metal alloy that would be? So the interesting thing is if you've got that low melting alloy, you can put it into obviously in room temperature. You can pass X-rays through it, do tomography, understand how this bubble flow happens in 3D. Do you know which alloy that could be? It was standing up there. Gallinstan. Go and have a look. Gallinstan. It's an alloy which has a melting point of minus 19. And interestingly enough as well, we now can understand the flow of bubbles at high density liquids, not just at water. The next step is take that information and put it into CFD models. So we have projects that are doing both, measuring and putting in CFD and understanding bubble flow through these liquids. You need to do this if you want to optimize processes. It's no use talking about circular economy, but you don't understand this stuff. So I'm just trying to show to you, we're not just doing the technology, we're trying to understand the depth as well. What are the important parameters? Don't look at these graphs. What is important is just the takeout. We have dynamic viscosity and surface tension. It affects the contact area. It determines how much splash is there. So the more splash you have, the more surface area you have for mass transfer and heat transfer. It affects the mixing time. It also determines the bubble surface area through which mass transfer can take place. Now, this is quite unique work in this sense that it's trying to understand that. And so it's once again, it's research, not for the sake of research, but to optimize and understanding the process. And importantly as well, the bubble sphericity. Is it a cap, bubble cap? Is it round? What does the bubble look like? And what is its effect on the mass transfer? So of extremely important as well is understanding the flame. You saw in that video the flame of the lance, because in some systems you have to add fuel. In sulfur-based systems, the sulfur is the fuel, so you would use that. But very important is here, we are also modeling that lance. But ultimately of importance is you have to understand what the surface of the oxygen pressure is, the partial pressure. Because if you want to do metallurgy, you have to know exactly the PO2 of that process. So what is, if I can ask, what is the partial oxygen pressure for typical matte smelting? Anybody want to? How many atmosphere of oxygen? And what is the oxygen partial pressure for lead smelting, lead sulfide smelting? These are typical information that is important for you to understand. And for matte smelting, say 10 to minus, say 9, depends on where you operate. Smelting, PBS smelting, 10 to minus 7. You operate 10 to minus 7.5. You have to understand that in relationship to the metallurgy, and you can fit that very well in the system. And that is the beauty of our subject. We can talk circular economy, but we can bring it down to a partial oxygen pressure, because that partial oxygen pressure tells you how circular we can ever get. We can scale the system. That's the uniqueness, and we can put it all in a big model. There are not many people out there that can do that other than us metallurgists in this room. So also interestingly, as I said, we are looking at, there are 50 thermocouples in our experimental TSL and Freiberg, understanding the flow of heat in the system. I don't want to bore you with these sheets. I'm going to sort of quickly go through them. I'm just telling you we're doing this stuff because you need to understand not only mass transfer, but also heat transfer if you want to understand the circular economy system. And some people out there in publishing in fantastic journals out there with high impact factors, they don't even use the word energy or exergy or entropy because they don't know the stuff. And they're telling us how to run our circular economy. Whereas you in this room are the metallurgists that should show the way. So here's some graphs, we can measure that. And I'm just leaving that there for the moment. So in summary, what I mentioned, if you understand the temperature, you are oxidizing or reducing, you can smelt a whole host of materials. The major elements are mentioned, and then on top of that are all the minor elements in the metal wheel. And you can deal with them in a smart way. At the same time, you look at the slag chemistry. I just drew some animated here, which shows to you, depending on the condition, your melting point, your liquidus changes. You have to know all of this stuff. These pictures were developed by FactSage. I drew all of this stuff in my free time, in my nerd time, between all the other stuff we did. So, in summary as well, to bring that, one of my students is actually doing some work together with FactSage, which is a very well-known simulation tool for thermodynamics in our field. He's just with them in Aachen at the moment in Germany. We've created a compartment model. We take information and knowledge which we know from here, plus our practical industrial knowledge, and we create complex FactSage models with us to understand how metals are distributing through the system. Once again, there's no such model around, to my knowledge, for TSL. There is a similar model for converters, and from steel side, also created by these guys at FactSage and GT Technologies in Aachen in Germany. But so we have taken that knowledge and created a FactSage model. Okay, now I've got another 1 minute for but I'm going to, I started 5 minutes late, but give me another 5 minutes and then I'm finished. It's an interesting example that wraps it up. I spoke very much about primary side. Let's go to the secondary side and product design. My colleague and I were contacted about 2 years ago. Can you calculate the recycling rate with your models of our Fairphone? Now, Fairphone is a modular designed phone. It's a Mickey Mouse, and it's a little midget against Apple and Huawei and also Samsung, these products. But they've got really a lot of guts because they're driving a bit the agenda, how to deal with design, how to do a sustainable product. So they don't only look at the product, but they follow the whole chain, material chain. So they are making sure that their metals and their mining is not conflict tainted. They have a modular design to change stuff, to maintain and keep it in your pocket for a longer time rather than us buying a new iPhone every half a year and we pay $1,000 for it, which is quite crazy. So this is simply what we've done. And remember I started off with the top bit of the flow sheet. Here we're now at the bottom bit of the circular economy. The company gave us their full bill of materials. They gave us, in other words, exactly how this thing was designed. What is connected to what? Which plastic, which glue, what the filler is in the plastic, what the plastic type is, what metal and alloy is connected to that plastic, the whole thing. We've taken that mineralogy and put it into HSC, the simulation software. In other words, with a design, we have a shredding or a physical separation model to understand the particles, and then we can put it into the different metallurgical flow sheets. Not only just copper, but lead, zinc, and all the other stuff, aluminium, steel, energy recovery for plastics, etc. So this is this bit over here, the physical separation. So we have a physical separation model that separates the different particles. And then we have a metallurgical, which is much more complex. Don't look at it, you can look at in your private time. But the point is, they gave us the bill of materials, which no company would ever do because of IP issues. But they did it. They just trusted us. But they just gave it to us to do in trust. And we've not broken that trust. Simplistically, we then could do different scenarios, different designs. We could understand and feed back to the designer what to do. One of the scenarios or one of the flow sheets that we then checked out was to take the 7 modules and put them each into the correct processing flow sheet. There was another option where you take the whole phone and put it in the furnace, which is also practice. Why? Because this, you can't take the battery out, because it's stuck inside here. This one you can take out. So how do you deal with that case and this case? And you can calculate that. And then there was the other case, which I'm not going to show to you, where you cut it up into and shred it and then sort it again. Just think of it in terms of entropy. If you have 1 particle, put it in a furnace. Have 7 particles and put it in the right furnace. Or cut up stuff into zillions of particles and then sort it again, and then put it into the right furnace, and creating dust, fine particles, sludge. It's a no-brainer. The question of design for recycling, this is a unique message, guys. This is, people don't think of it that way, but this is what I realized out of this simulation. What is the optimum module number for any product? For a wooden chair, it's 1 module. It's the chair out of wood. What would it be for this type of product? What would it be for that type of product? And it's quite simple to do. If the design could just pass the mineralogy to a simulator like we have, we can calculate it. But what happened, we presented this, there were some OEMs in the audience, they said, no, we don't want to, it's too difficult. They obviously don't want to hear the truth. But these guys did. The truth is, I don't know if you've seen this example, but what is the recycling rate from a mass base of this? What would you think it is for this telephone? Take a guess. Have you ever thought about it? You're all metallurgists, you walk around with this. Not so. So the critical question you should all ask yourself is, hey, how sustainable am I as a metallurgist? So I don't know what I know what it is for this, but I can't say it because I've not. But I can say it for this. We've published this. Take a guess. Give a number. 100%, 0%, 30, 50, 60. Okay, you're too shy to say. Here, 30. Now that's pretty amazing. This product got a prize from the German government for sustainable design in 2017 or 2016. Most innovative product. Nobody had done these calculations, but these guys had the guts to do it. And they put this on their webpage, which is quite a lot of guts. Now this is, the beauty of the message is here. You guys, we as metallurgists have to have the guts to stand up and change the world. These guys are trying to do it. There are a lot of guys just creating a lot of smoke and mirrors. And you can't get to the truth. But anyhow, the other message, what can you see here? You all know the energy label in a product. So my colleague and I just put it on its head and came up with this scale and said we go from 0 to 100%. If you look at the energy label, it sort of hangs in the air. It's not really exact. Here it is exact, and you can get that number. So Now I'm at my second last sheet. The interesting thing is I got a call from Greenpeace, of all places. Greenpeace phoned me, and they wanted to know what does this all mean, and I later realized they were busy with this report on green design, Guide to Green Electronics, which you can see here as a document you can download. You see where Fairphone sits. This document was written in San Francisco. That gives you an idea what's behind this, okay? So we have Fairphone ahead of a lot of very well-known names. Why? Because they're doing the right thing. They had the guts also to do what we did, and the work that was actually done, I showed to you, was actually cited in this document. And I think for the first time, really, metallurgy is getting into this field in a really digitalized, hardcore way that you can make a good decision. Okay, so my last sheet is quite with a message. We talk about circular economy. We speak about circular cities. We have all these smarts and nice words. But the main message I gave to you is the following one. A circular economy needs a smart, adaptive processing system. It needs a metal wheel to deal with. Without it, circular economy is, at least in a European concept, is just nice music. We can have some cocktails and feel all warm and fuzzy around the heart and go and do all that type of stuff. In the end, we need this. At the end, we also need to understand how these material flows work together, and therefore you cannot use Excel sheets. You need to go to simulation models to do that well. Obviously, we have to understand energy, which is linked, so we come to the circular economy picture. Materials, the metal wheel, and then energy encapsulating it. We can't forget the mine. Why not? Because we still have population growth, we still have urbanization, we have usage of metal that goes into urbanized societies. But we also have losses, as you see. Complex products have a lot of losses. So you need the mine. You can't just do away with it and hope for the best. We need obviously also to understand water. If I do a life cycle assessment, I do a simulation. It's not just materials and energy, there's also the water flow sheet that goes through that system. So at the same time, as I deal with materials, I can also deal with water footprint, which is obviously a very valuable commodity. We just know now, and we see how we've mucked up the oceans with all this plastic that floats around there and all the dirt that we've created. We will future have nice buzzwords like smart mobility and e-mobility and all this stuff. But it needs the metals from that to deal with it. Not only to feed in, but to feed back. We have all these cities around us, and ultimately also Industry 4.0, which is a buzzword as well, but it's only a part of the system, a small part of it. It's once again fed by the materials that comes from here. When this gets obsolete every 4 years or 3 years, whenever we have to change stuff, where do the metals go? Is there an infrastructure that can actually create new robots, new computers, can deal with the junk and reprocess it and bring it back here? Those are the questions we have to answer. So, now I've done my bit, and I said I would be shorter this time than last time. So I'd like to leave it here. If you have some more questions for me, we can discuss now, and if not, you'll get the sheets. My number is here if you want to contact me. I'll be happy to answer your questions. Thank you.